Okay, so today is about solving for missing segments within similar triangles. So in order to do that, the first half of this lesson is going to be about the fundamentals you need to know and understand from a geometry standpoint, of course. And then the second part of the lesson will be the application of that. So first, the basics. Somewhere in middle school, I'd be lying if I told you when, you were taught how to solve a proportion, all right, where if you have a ratio, some number over some number, right, a comparison of two numbers, A over B is equal to C over D, then A times D equals B times C. So your teachers at that level probably did something like this. They circled it that way, they circled it this way. Some people call it a butterfly method, but generally speaking, you're talking about what's referred to as cross multiplying. All right. Now, cross multiplying is generally considered the easiest way to solve a proportion, so I would recommend sticking with what works. All right. So if we were looking at these two, just basic algebra here, but we got to make sure we're okay with it. If you had x over 5 is equal to x plus 2 over 15, you're going to cross multiply, so x times 15 is 15x. Do not lose your equal sign. Once you multiply these two pieces, you have to remember to put your equal sign in the middle. And then 5 times x plus 2. Most kids skip this step, but most kids also mess it up. You're 5 times x plus 2. I think you should write it. I make my honor students write it. Then go ahead and distribute after that. 15x is equal to 5 times x, 5x. 5 times 2, 10. Then from there you'd solve. Right? I'm not going to waste too much time going over the basic algebra, but that would give you 10x is equal to 10. You would divide both sides by your 10, and x is equal to 1. All right, now, is it checkable? Of course it is. Same concept here. 8 times, well, you can start with whatever ones you want. It doesn't matter which one you go first. So I'm going to do 8 times x is 8x, and then 3 times x plus 10. So that'll give me 8x equals, distribute, 3x plus 30, minus my 3x from both sides. Let's get all those x's on the same side. 5x is equal to 30, divide, and x is 6. All right, so that's how you would go about solving a proportion. Okay, so that was the first half of the reminder of what, the fundamentals that everything's based off of. Second part of it is remembering what similar triangles are. So your similar triangles are the result of dilations, all right? And you recall that dilations usually change the size, but they change the size proportionally, all right? You may even remember how you did similarity proofs, where just like we had 5 ways to prove the triangles were congruent that we just covered, you probably focused on one main way to prove triangles are similar, which was angle-angle congruent to angle-angle. Though there was side-angle-side similarity and side-side-side similarity as well. So the key to this is when you have similar triangles, you're going to wind up having the corresponding angles will be congruent. The triangles are just bigger or smaller versions of each other usually, but the angle measures of the corresponding angles are still equal. They match up exactly. The key to it is that the sides, the corresponding sides, are going to be in proportion. All right, so when you're dealing with similar triangles, your corresponding sides are in proportion. So, you're going to have to know how to write the proportion. That's the key. All right? If you can look at it and you can write the proportion, then solving it's just like what we just did. All right? So, you're going to have to focus on matching up the corresponding sides. So, I would think you can see the two triangles here. Right? You got the little guy, CDE, and the big guy, CAB. Now, I have to tell you right now, I'm giving you that triangle CDE, maybe you remember the symbol, is similar to triangle CAB. All right, so if that's the case, now that you know the triangles are similar, right, now you can go ahead and say, oh, then I know the sides are in proportion. So there's a bunch of different valid proportions that exist here. So you're gonna have to make sure that you're writing one that makes sense. Now, ordinarily, I'd have an X somewhere here, or I'd be saying, hey, solve for side AB. So I'm not going to say that right now just because I want to talk about the theory. But if you match up the corresponding sides, like CD, so that's this side of the top triangle. You see how it was like a dilation that pulled this out. So what's the corresponding side of the bigger triangle then? All right, so like if you're looking at CD, that goes with CA. All right, so you could write the ratio of CD over CA. And then you can set that ratio equal to, maybe you're dealing with CE. And that's going to match up with CB. All right, so you can say that's equal to CE over CB. Now, in this case, I ignored these two, but maybe they were part of the problem. All right, but for right now, just focus. So this was like this CD, this in this case, the left side of the top triangle over the left side of the left side of the small triangle over the left side of the big triangle is equal to the right side of the small triangle over the right side of the big triangle. Because the way this dilation played out, you can look at it as both of them being on the left because those were the corresponding sides, but you have to make sure you got flow. I had small triangle over big triangle, so I have to have small triangle over big triangle. All right, and for that matter, nothing not to neglect here, you could have even written DE over AB, but you would never write all three. You would just be picking two. Whichever two work for you, whichever two ratios work for you for whatever the problem you're dealing with is. All right, so I'm going to take a pause right there. We're going to apply two different problems, and hopefully it'll make sense for you. All right, and as always, any questions, hit me up in the discussion board.